Winter can be a time of special beauty, but it can also serve up conditions that severely threaten man's civilization. In either case, whenever the thermometer falls below 32 degrees Fahrenheit, steam users, especially in outdoor situations, face the possibility of frozen lines and freeze-damaged equipment. When steam condenses, it becomes water, which expands when it freezes. Any vessel containing the water must also be able to expand, or it will rupture or shatter. Even if traps, valves, lines, or the like aren't damaged, the ice will impede steam or condensate flow in the system. Therefore, in any sub-freezing environment, condensate must be removed from a steam system, regardless of its operating state. There are a number of piping guidelines considered to be good practice in freeze-prone environments. First of all, don't oversize the steam trap. Trap discharge lines, tracer lines, and heat exchangers should all be pitched to allow gravity drainage. Traps and lines should be insulated wherever possible. Return lines that cannot be insulated can be traced to prevent freezing. When traps discharge to an open drain, the discharge lines must be kept short. Condensate may freeze in long lines if the trap's output flow is very light, or when there is a long period between the discharge cycles of an intermittently discharging trap. Avoid low points in discharge and tracer lines and in coils. When it is impossible to avoid low points, provide a safety drain to prevent freezing when steam is turned off. But even if these rules are precisely followed, there is still a factor sure to bring on the problems associated with freezing, and that is that no trap will drain completely. In the demonstration lab, we can look at several types of traps and observe the characteristics which prevent complete drainage into open drains. This bimetallic trap is operating properly. Note the backup of condensate and the continuous discharge. Now we'll turn off the steam. Bimetals are designed so that rising temperature generates a larger pull by the bimetal to close the trap against the normal operating differential pressure across the trap. When the inlet pressure is lost, the bimetal pulls the valve to the seat, where it remains until the strip cools. Upstream, steam condenses, however, forming a vacuum which holds the valve closed, even after the bimetal cools. In an environment where freezing could occur, the inlet to the trap would be restricted or blocked completely, and the line or the trap could be damaged. Intermittent drainage cycling is the normal operating mode of thermostatic bellows traps. When steam is turned off, condensate flow stops. The liquid inside the bellows causes it to contract and open just below the saturation temperature of the inlet steam pressure. When the steam is shut off, the opening temperature point drops with the inlet steam pressure. The bellows temperature stays high, however, until the liquid in the bellows cools, so the trap remains shut. Steam condensing ahead of the trap forms a vacuum which prevents condensate drainage through the small trap orifice even after the bellows cools and contracts, opening the valve. If the ambient temperature at the trap were 32 degrees Fahrenheit or below, we would have frozen condensate and all of its accompanying problems. Here we have a normally operating disc trap, and again notice that the drainage cycle is intermittent. When the valve is closed, condensate backs up. When steam is turned off, this condensate isn't immediately purged. The disc trap is held closed by the flash steam pressure above the disc acting upon the total area of the disc. In order to open, this force must be overcome by the sum of the inlet pressure acting upon the inlet port and the outlet pressure acting upon the discharge groove. When the inlet steam pressure is removed, the opening force drops quickly. The closing forces, however, remain high until the steam in the control chamber is condensed by radiation, bled off through a controlled port, or both. Before the control chamber pressure decays sufficiently, the steam ahead of the trap condenses, eventually forming a vacuum. A vacuum on the inlet side of the disc trap causes the trap to act as a check valve by sealing the disc against the seat. Again, In a freezing environment, blockage and damage would likely occur. Mechanical traps, such as inverted buckets and floating thermostatics, are continuous drainers. They do not back up condensate. When the steam is turned off, the condensate drains from the line ahead of this IB to the level of the valve. However, water retained in the trap body will freeze if the conditions are right. Thin-wall stainless steel IBs are resilient. They expand when condensate, which is trapped inside them, freezes. Once these traps have been thawed out, they return to normal operation. Condensate is now a valuable commodity. Virtually all new plants are designed with condensate return systems, and many older plants are retrofitting condensate returns. Flash recovery systems usually result in pressurized return systems. Any back pressure in the system only serves to quicken the reversal of differential pressure at the traps, increasing the likelihood of freezing when steam is turned off. So there is no such thing as a self-draining steam trap. Bimetals, bellows, and discs close when steam is turned off, retaining condensate upstream from the trap. Mechanical traps drain the lines, but hold condensate in their bodies. In addition, some low points in steam tracer and condensate inlet and outlet lines are unavoidable and retain condensate when steam is turned off. In order to prevent costly damage and process interruption, either temperature or pressure-actuated safety drains are required to drain these lines under shutdown conditions. Process heat exchangers, which are in potentially freezing environments, have large drainage requirements, large lines, and often operate with modulating steam pressure control, which requires low-pressure operation. For these applications, temperature-actuated safety drain devices should be selected. The temperature-controlled devices sample condensate temperatures in their bodies. If this temperature falls to a preset low limit, the sensor opens a valve, draining the system before it can freeze. Rising temperature closes the valve again, and the system resumes normal operation. Drip and tracer lines and their condensate loads are normally quite small in comparison to process applications. When steam is shut off, the pressure in the line falls rapidly compared to the condensate temperature. Collapsing steam forms a vacuum, which would impede drainage after the condensate cools enough to open the safety drain's valve. In this application, the less expensive pressure-actuated safety drain is recommended. These devices sense the pressure in the system and open when it drops to slightly above atmospheric. The Armstrong pop drain is a spring-opposed, pressure-actuated ball check valve. Above 5 psig, the line pressure holds the valve on the seat. When the line pressure drops below 4.5 psig, it is overcome by the spring tension, which forces the ball from the seat, opening the drain. Since the valve opens against a slight pressure, condensate is pushed out of the lines and traps, and no vacuum can form to prohibit drainage. When the steam pressure is restored and the line reaches 5.5 psig, the force of the spring is overcome, closing the drain. Regardless of the type of actuator used, correct placement of the safety drain is essential for reliable freeze protection. Safety drains should be used at low points of horizontal or vertical tracing lines and immediately upstream of any vertical projections which impede gravity drainage. Any thermodynamic or thermostatic trap which discharges to atmosphere should have a safety drain at the low point of its inlet piping. In addition, if these traps discharge to a closed return, a safety drain should be applied to the low point of the outlet piping, since the traps will close when steam pressure is lost. The valve of an IB is open when steam pressure is lost. Therefore, a single drain will empty both inlet and outlet lines. The body drain of a side inlet, side outlet IB is a convenient installation point. Multiple trap manifolds not only reduce installation and maintenance costs and procedures, but provide a means for freeze-proofing your system more easily and less expensively than with large numbers of single traps. Insulation of groups of lines is easier to apply and requires less material. The heat of condensate and flash steam from a branch main drip trap can be used to prevent a station from freezing when that section is shut down. A technical report titled A Guide to Steam Trap Installation for Freeze Prevention and a number of videotapes referring to specific freeze problems are available through your local Armstrong representative. He is willing and able to assist you in determining the proper application of steam traps and related equipment in freezing environments and can help save you countless dollars in maintenance costs and unnecessary downtime.